All right, everybody, welcome back. So today's lesson is itself pretty short. We're kind of at the point of the semester where next week we're going to launch into something new. And so there's a few more things that we need to clean up today, tomorrow, not a huge amount. But we're just sort of like coasting a little bit, giving you guys more practice in the homework, preparing for next week's midterm, which will be on Tuesday. But on Monday next week, we're going to kind of shift gears and launch into a completely different conversation about Java's object model, which will consume us for kind of the middle third of the class. So that's why today and tomorrow's lesson are actually the last couple lessons. I would argue are in sort of enrichment, right? Today's lesson, though, does provide you with a new a new feature of Java that you can use in your programs. It's kind of cool. Nice to see Java evolve a little bit. So I'll be happy to take questions about that. Anything else that might be on your mind today. But we can get this short if that's if you guys don't have too many questions. Happy to go over recent homework problems, talk about last couple lessons. Talk a little bit about new Java features. We can maybe look at some of the other new Java features that have come out if you guys are curious about what's been happening in the last couple releases. We can talk a little bit about where those features have come from. What's driving some of this, because part of what I would argue what's driving sort of recent Java evolution is other languages that have emerged that are competing with Java. It's this happens all the time in software, right? When you don't have any competition, it's easy to get complacent, kind of just keep doing things the way you've been doing them. But once a competitor rolls into town, sometimes that causes you to kind of, wake up a little bit and be like, oh, okay, someone started to eat my lunch a little bit here. I need to shape up and start to evolve a little bit and adapt and innovate a little bit. And I think that's what's been happening in Java. So again, we can talk a little bit about that if you want. But I'm here, you're here, happy to take questions. Hope everyone's doing okay. So yeah, I take questions in the chat, also on the forum. That's a place where you guys would like to ask. But I'm here and I don't have too much to cover. So, but like I said, the topic of what's going on in the world of Java is an interesting one, and certainly one that I would be happy to talk about if that's what you guys would like to talk about. So anyway, I'll hang out for a few minutes to see if there's any questions. If not, I may just let this one wrap up a little early. I hope not, because it's fun stuff to talk about, sort of the evolution of Java. But I'll sort of let you guys drive that conversation. So I'm here. Great question. What makes languages more powerful than other languages? Okay, so I like that question quite a bit. I'll try to answer it. Let me point you. One thing I will put in the chat here is an essay by somebody named Paul Graham. Now, Paul Graham, people feel differently about Paul Graham. I'm not defending everything about Paul Graham. He is a fairly significant figure in Silicon Valley. He started Y Combinator, and he was, I'll get to that question in a second after I finish rambling about programming language power. So Paul Graham, again, very famous innovator, started Y Combinator, which is a startup incubator. It's very famous. A bunch of really famous companies have come out of that incubator. Also, one of the people who set up Hacker News, which is a big news aggregator site that publishes a lot of stories that are of interest to people in technology. The essay that I posted is long and worth a read, because he essentially makes this argument that there is a power spectrum in languages, which I don't think anybody would disagree with. Although what people tend to like to argue about is where their favorite languages fall on that power spectrum, right? And then he has this really fun story about how he and some, of his buddies built a company that did kind of built websites, I guess, for people. I don't know exactly what it did, but it was implemented in a language called Lisp. So Lisp is a language that many people Lisp, and it's a scheme family of languages, is a family of languages that many people teach in university settings, but as he points out, a lot of people don't consider it practical to use in the real world, but it is. They built a whole company doing it, and so that's a sort of. But as far as power spectrum for languages, I think there are features and capabilities, and particularly sort of certain levels of abstraction or ways of thinking that that higher level languages enable that lower level languages lack. It's a great question. I don't know exactly how to measure it. And one of the things that Paul Graham points out in this essay, which I think is a really important thing to understand as a computer scientist, is he points out that when you're unfamiliar with languages that are higher on the power spectrum, you tend to not understand their more powerful abstractions. So, when somebody has learned like C their whole life and they look up at Java or Rust or things like this, they may not understand the power that these languages are providing, and these things look strange and unfamiliar to them, and so they kind of stick with what they know. And this can become in many ways a trap, right? Because it forces you, it puts you in a position where, because you don't understand, people don't try stuff, so they don't understand it. It feels unfamiliar and weird at first, and then over time you get used to it, and you do start to enjoy things. But I mean, to me, I think as someone who does a fair amount of software development, I guess I think of power on two levels, right? One is how, there's this frustrating disconnect a lot of times when you're writing software between having an idea about how you want something to work and getting that idea actually implemented. And some of that's you, right? Some of that's just your slowness, your rustiness. But what you start to realize after you do this for a while is that some of that's the languages that you're using and the tools that you're using. And them either getting in your way, slowing you down, or sometimes sort of accelerating the process, right? Helping you, right? Guiding you towards particular patterns that end up allowing you to build the things you want. Again, like I can, it's like, people are, just to use a silly example, people are asking for like new features on the 125 website, and it's like, I know how to do it, right? It's a question of how long is it going to take me, and how many other mistakes am I going to make along the way? And I think better languages tend to accelerate that process. The other thing, though, that I think about when I think about power is sort of satisfaction from my perspective, right? So when you develop software, when you work in computer science, you want to feel good about what you're doing. And I think good languages make you feel good about the code you write. When you solve a problem, it's like, yeah, that's cool. I feel confident about what I did, but I also feel joy and pleasure in what I wrote. And languages that force you to do things, I've been encountering this because I've been doing some development in TypeScript, and I can get things to work, but I don't feel that happy about it when I'm done. It doesn't feel clean and beautiful, right? The code that I wrote, it may work fine. I always keep reminding myself that, right? It's like really how it impacts the students in the class that matters, not how I feel about what the code looks like, because nobody cares. As long as it doesn't crash all the time, which sometimes is a problem. But there is this aspect when you spend a lot of time writing code of just wanting to feel good about what you're doing, right? And feeling like certain languages and certain tools enable that, right? Like, so, and again, and this is just a completely personal thing, but there are certain languages that when I write them, I just feel happier. Like I feel better about the hours I spend on it. I just walk away from it. I'm like, yeah, that was good. I feel like I really did a nice job with that. And there's other ones where it's like, well, I got it to work, but God forbid that I ever have to go back and look at that again. So anyway, great question. We can talk about that more, maybe offline or on the forum or in office hours at some point. There'll be. I think I'll put a few questions. Well, that's a great question. Maybe we won't have questions on coders on the midterm. I'll think about that. Probably not. The midterm has a different balance of questions. So the midterm has like probably 4 programming questions, and then a smaller number of multiple choice questions, but they're worth more points. So it's just a little bit of a different mix of questions. Let me go back up the stack here. So, question about compilation. Yeah, exactly. So that's what the compiler is doing. The compiler is taking the source code that you wrote and it's transforming it into a format that the Java virtual machine knows how to run. If you were compiling another language, so I'll kind of merge this with another question, right? Compilation process is the same for all languages. There are many languages that will compile code. The tool that compiles code is different for each language. So every language has its own compiler, right? Because to some degree what defines a language is the source code syntax. And so if you try to, and you could try this like with one of our playgrounds, if you type Python code into our playground and try to run it, it's not going to work because it's a Java compiler that speaks Java, right? And so if you give it Python code, it may be completely valid Python code, but you're not talking to Python, right? You're talking to Java. So you got to speak Java. Does every language have a compiler? No. Some languages don't have a compiler. Some languages will directly take the source code that you wrote and execute it. And again, that's kind of what Python does. You can think of Python as working that way. And so, not every language has this compilation step, although there are many languages that do have a compilation step. And again, off the top of my head, I think I can think of more languages that have a compiler than that don't have a compiler, but they both exist. Now there's another sort of, so the output of the compiler is different for different languages as well. So there are languages like if you take C code and you compile it, what you end up with is something that an actual computer processor knows how to execute. So what you have is a series of instructions that like an Intel CPU, for example, can actually run. Okay, so this produces something called machine code. It's a code that can be run by an actual machine. Like you could buy, on Amazon or on Newegg or whatever, you can buy a computer processor that is capable of executing the instructions that the compiler produced. With Java, there is no such computer chip that you could buy. There's no computer part that will execute bytecode. Instead, what happens is that there's this other program, which is called the Java virtual machine, that we run when we run Java in the examples that we did a few days ago. And that takes that bytecode and translates it again into code that the computer can actually run. And why there's this two-step process is, so if you look back at the history of Java, one of the Java slogans, and in fact I meant to put this essay up. That's the other thing you gotta love about Paul Graham is that his website is old-fashioned. Let's put it that way. I don't want to get in trouble. Maybe he'll watch this video and get mad at me, and I'll never be invited to. I'll never get a startup into Y Combinator. But old-fashioned, shall we say, about the website. What was I going to do? Oh, right. I'm going to look up Java version history or even just like let's look up Java history or Java programming language principles. Let's see here. Right, where's that? Write once. Here we go. Yeah. So this idea, write once, run anywhere. What does that mean? So the idea is that at the time, and it's interesting to see how this, again, the world of computing has continued to evolve, and so some of these concerns are a little bit different. But when Java came out, and this is still true, though it's true for different reasons, but in the past, and actually this is going to be true again. So this is a fun question. In the past, like when I was in school, you had Intel processors and there were PCs, right, which ran Windows typically, that used Intel microcontrollers. So on some level, those Intel CPUs, they speak one language. And so when you compile to machine code, you would have to compile to the language that processor spoke. There were, and there are still other completely different types of computer processor that speak different languages that understand different types of machine code. So for example, today, the most frequent place you find one of those is on your phone. So your desktop or your laptop, if you have one, probably has an Intel CPU. So Intel CPUs use a specific set of instructions. It's not very different than bytecode, but it's different. They're very simple. Right? When we looked at bytecode on the previous video, or yesterday in this lesson or my walkthrough, we kind of looked at very simple instructions like add, subtract, move things back and forth between two different places. Machine code is not that different, but so your Intel processors that have a particular type of machine code. If you look at your phone typically runs what's called an ARM processor. That uses a completely different set of instructions. So the processor on your PC and the processor on your phone don't even speak the same machine code. They don't even use the same set of machine code instructions. So if you compile something like C code, right? Let's say I take C code and I compile it. What I get is machine code. But when I compile it, I have to decide, am I producing machine code that runs on my desktop or machine code that runs on my phone? Because that's like two different outputs of the compiler that are totally different, right? Again, it's not, it's like translation is not a bad metaphor here, right? So if I had a document and I needed to have it translated, I might have a translator, the compiler, that knows how to translate into two different languages because my phone and my desktop speak different languages natively. So when I take my piece of source code and have it translated, I have to choose. Now I can have it translated twice, but imagine that I have like a bunch of different devices that speak different languages. Now this is starting to get problematic. And so one of the goals behind Java was I'll only translate the code once into this thing called bytecode. And then I'll have this little program called Java. And the Java virtual machine is quite simple. And everybody will install that on their computer. And then that program will allow you to run the output of the Java compiler. And so it's a different model for distributing programs, right? Rather than having to compile the program a bunch of times so that it can run on different CPUs, I compile it once, but I don't compile it to machine code, I compile it to bytecode. And then everybody who wants to run it installs this little program called Java on their computer, and then you can run the code. So that was the model. Now, what's interesting, there's some interesting things that have happened since then, right? One of the interesting things is that at some point, so it used to be that Mac ran a different type of processor. So Mac laptops, like when I was in college, a Mac laptop ran a different style of processor. It did not run Intel processors. And so, and they had their reasons for this, and they had ads about why it was better and stuff like that. But now at some point, I can't remember when this happened, but Apple decided that they were going to use Intel processors for all of their laptops, right? And they did this for, I don't know, maybe a decade. Some of you may have seen that just recently, Apple announced that they're actually moving back away from Intel into their own processors. So they're actually going to, Apple's going to start actually making their own processors that they're going to have in future laptops and future Mac devices. So that's, to me, kind of like a fascinating development because it's a kind of a reproduction. It's you had an ecosystem of two different, it used to be Mac and, people do use Linux, but Mac and Windows sort of dominate the consumer marketplace for operating systems and for sort of primary computing devices other than phones. And so you had two different types of processor in the past. They came together for a while. Everybody was using Intel. And now there's this new bifurcation, and you're going to have two different types of processor again. And in the meantime, you've also had people start to use phones, which use a different style of processor. And so, it's never really, we never got to the point where every single processor, or even the majority of processors out there in devices, was speaking the same machine code language. And so Java's approach to compiling to bytecode and then using this thing called a virtual machine that kind of runs that bytecode was designed as a solution to work around this. Now again, that solution is 25 years old, and in the meantime, there have been other things that have allowed people to run stuff. One of the primary ways that people execute code these days, even though you don't always think about it this way, is through your web browser. Your web browser runs code. Every time you go to a web page, there's code that's running on your computer. That code is in a language called JavaScript, which is completely different than Java. But on some level, so Java tried to solve this problem of write once, run anywhere in a particular way. But what happened alongside of it is that everybody installed a web browser on their computer. And so now we have this other model of write once, run anywhere, which is that if you can deploy your code and it can run on a website, then everybody with a web browser who wants to run it can go to your website and run that code. And so this is how, stuff like, I don't know, all of the apps that you guys use, all the Gmail type stuff, any sort of embedded email, Office 365, to try to be fair to everybody, Facebook, even if Facebook has an app for the phone, but you don't have to use it. You can actually use Facebook in the browser on your phone, and you can use it in the browser on your desktop. And when you use that, Facebook's almost like an application at this point, right? But the code that is being run on your computer is JavaScript that was delivered to you by the browser. So this is kind of another way that we found in technology to accomplish this write once, run anywhere sort of goal, right? So anyway, this stuff's it's fascinating, right? Like even within my lifetime, and I'm sure that people that are just getting started now, you guys are going to see these huge shifts in technology within your lifetime, and it'll be fun. It'll be fun to watch, right? And it's also something that if you're thinking about starting off on a career in technology, just to keep in mind that this stuff changes all the time, and on some level that can sound a little frustrating because it's like, oh, I just learned Java, and now you're telling me I'm supposed to learn something else, and that's kind of like how stuff goes. There are niches that you can get into in technology where you can kind of do the same thing for a long time. But, particularly if you want to kind of keep working on new problems and stuff like that, you'll find yourself over time learning new tools and new languages and new systems, and the world keeps creating these things, right? And it's just a really exciting field to be a part of, I think, for that reason. Other questions? Let's see. Yeah, we can go through the Sudoku problem. Best way to study for the midterm, go through the homework, go through the lessons. Those are the best approaches. As far as reviewing the quizzes, we may put up the programming problems in the quiz, but I'm not going to post the multiple choice questions from past quizzes. Those are just sort of entirely for evaluative purposes. And they're hard to write. We tend to reuse them. And so in the past, that's not something that we've released. The programming problems, we may put those out there for you guys to work on, but the multiple choice questions are not going to be publicly available. All right, so let's spend a little time on Sudoku. Hopefully you can sort of guide me here as far as working through the solution. So was there a particular part of Sudoku you wanted to review, or is there I suspect there was kind of a specific spot that you might have found confusing. I'm trying to think of, do I have let's see if I can find a piece of paper here. Okay, I'm gonna have to order that little mini whiteboard that hold on a sec. Maybe I can find an online Sudoku. It's a board. I just want the board. Let's see here. Okay, here we go. Let me move this to the other thing so you guys can see it. I want to go to the other one. Let me pull up a blank Sudoku grid. All right. So, the first thing we want to think about when we're doing Sudoku is, okay, fair enough. That's a great question. Why are we creating this Boolean array, right? Well, so the Boolean array is there so that we can keep track of what numbers we've seen, right? And so this may not work out particularly well. I really want to, I really wish I had a different type of, I don't even know what it would be that I could mess with. But so the purpose behind the Boolean array is, imagine that I'm going down. So the way the algorithm works is I first scan down each column, right? So I'm going I do that, I'm going down, down, down. I do that 9 times. And then I go across, each row. And I could do these in either order. In fact, I can do any of these steps in either order. I could do the rows first, I could do the columns first, I could do the subsquares first. So I go across the rows and I go I go across each row, okay? And then I go through each subsquare, right? I go to the top subsquare, right? And then I go through this subsquare, and really the way the algorithm looks is it probably goes like this because I'm using 2 loops, right? And the idea is that, in order for the Sudoku board to be valid, right? In order for the solution to be cracked, every column, every row, and every subsquare has to contain all of the values 1 through 9. So, the first thing that we kind of do when we solve this problem is we think about movement. Like, how do we move through the board, right? And that's a certain amount of what we do as part of the solution, is just set up like the part of it that goes, across the rows and down the columns and through the little subsquares. But then we also need to figure out, like, as we travel, for example, down a column, how do we keep track of the numbers that we've seen, right? Because essentially every time I get down to the bottom of a column, or every time I get to the end of a row, or every time I get through one of the subsquares, I need to stop and make sure that I've seen all the numbers that I expect to see. So what if that subsquare contained, only the number 1, right? So 111, 111, 111, right? So for example, let's say that this was my Sudoku board, right? Right? So this is not valid, right? Because this is, I'm not going to submit this because, it says, yeah, this is really bad because I'm only supposed to use 1 once in this entire subsquare, right? And I'd have a similar problem if my column looked like this, right? Or my row looked like this. I'll get rid of these guys if I can. And so it's going to check this. Yeah, it's going to complain about that, right? And so when I'm checking this, let's do a more realistic one. Let's say I did 1, 2, 3, 4, 5, 6, 7, 8, 9. This is going to be, it says it has multiple solutions, right? So this is going to be, this would not be a valid. This would be a valid row, right? This is not a valid board because I haven't filled it in yet, but this is a valid row because it contains all the numbers 1 through 9. But now let's imagine that I have a number that's included twice. So, how do I know that, right? I get across the row, and at this point, after I examine this last cell in the row, I need to make a decision about whether or not that row is valid. And so this Boolean array is entirely designed to make that decision. And so the way it works is I set up a Boolean array of size 9. When I initialize a Boolean array in Java, all of the values will start off to false, which is perfect. Because the idea is imagine when I get over here on the left, I set this to all to false. And the way I do that in my solution is I just reinitialize the Boolean array to a new array of Booleans because that new array will initially contain false values. And then I move across, right? And the idea is the initialized array that contains all false represents the state where I haven't seen any of the numbers. As I go across the row, I mark each, and you can think of just doing, doing this, like if I was like keeping track of this if I was trying to validate a board and this is like the back of a birthday card, but whatever. I had a little thing where I was keeping track of which numbers I had seen. I might have a little grid that was like 1 through 9, and I would put little check marks next to the numbers as I went. And then when I get to the end of the row, I look at my little, thing and I say, okay, do I see checks next to all of the numbers? If I do, I'm good, right? Because that means I've seen all the numbers 1 through 9. The way that I do that in my computer program is in this Boolean array. So the Boolean array, you can think of it like a series of checkboxes. The position in the array corresponds to the number. So when I see the number 1, I'm going to check off I'm going to set the Boolean at position 0 to true. Now, why am I using position 0? Well, this is just, because array indexes start at 0. So if Sudoku had been designed by a computer scientist, it would use the numbers 0 through 8. But clearly it wasn't, so it uses the numbers 1 through 9. And so we just have to make a small change to fit those into our array of size 9. And the change we make is we just subtract 1, right? So when I see the number 1, I mark. So let's imagine how this would work. I start off with my Boolean array. It's all false. I see the number 1. I change the value at position 0 to true. I see the number 2. I change the value at position 1 to true. Number 3, I change the value at position 2 to true. So now at this point, my array contains 6 false values and 3 true values at positions 0, 1, and 2. I keep going. Change position 3 to true. Change position 4 to true. Change position 5 to true. Change position 6 to true. Change position 7 to true. Now here where things are interesting. So here what I'm going to do is I'm just going to do the same thing. I'm going to set position 1 or position 0 to true again. Okay? And actually, now that I think about it, there's a little optimization that we could have actually made here. So maybe I'll go back and do that. But the idea here is that for now, I'm not doing this optimization. I just set things to true as I go. But when I get to this value, what's going to happen is that the value that I set to true in the array is at position 0. It's already true because I already set it to true here. Now what I do is I check the array. I go through my array of Booleans to make sure that they're all true. Because if I've seen, I have 9 slots in my array, and I've got 9 different numbers that I could potentially look at. And so if I've seen every one of those numbers, then it's a valid row, it's a valid column, or it's a valid subsquare, depending on what part of the board I've traveled through. If I find a false value, what it means is that there's some number that appeared twice because there was another number that didn't appear. And so what would happen here is I would go through my array and I would say position 0, true. Okay, good. Position 1, true. Position 2, true. Blah, 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 blah. Position 8 is still false because I never saw the number 9, right? This row does not contain 9. And so I get to the end, I check my array of Booleans, I see that there's 1 missing, and I can immediately conclude that this board is invalid. Okay, so that's the idea behind the array of Booleans. And I use that same array no matter whether I'm going across through a row, whether I'm going down through a column, or whether I'm going through a subsquare, right? It's the same idea because in each case, I've got 9 grid cells that I'm examining the values of, and I have 9 numbers that I'm looking for. I'll go back and do that in code with you in a minute. Are we going to release a quiz average? No. Well, maybe we will, but actually, sorry, I should answer that question differently. We will probably release a quiz average. It doesn't matter. This course, your grade in this course is not determined by anybody else's grade in this course. So, don't, there's no point in this class measuring yourself against somebody else. I have an unlimited number of A grades that I give out, that I can give out, and, there's just a fixed threshold, right? You get across that, it doesn't matter whether or not you're the only person or whether or not the most of the students are also there with you, right? You're going to get the same grade. So the average on the quiz does not impact your grade in any way, shape, or form. It just doesn't. All right, so let's look at, let's go through and do that bit because I actually have kind of a more clever way of doing this, right? So now, all right, let's get rid of this. So let's look at this. So, and this actually has a slight bug in it that I still need to go back and fix, okay? So, and I'll get rid of this too, okay? So here's an example of doing either a row or a column, and it depends on what our 2 indices mean, but it doesn't matter. And so here's what happens, right? So essentially, I'm going through, I set up a loop. So this is the loop that takes me through each row, and then this inner loop takes me across. Let's say that let's say this works out, so I'm going across a row. But again, it doesn't matter. What I'm doing here, I reinitialize my Boolean array seen to a new Boolean array of size 9, and then here's the part where as I go across the row, I use the value of board ij, and remember, I've already checked the board in a previous step, so I know that this number is between 1 and 9. I subtract 1, that gives me an index between 0 and 8, and I set that to true. Then what I'm doing here is I'm going through, and this should be K2. Sorry, this is the bug. I go through that array that I created up here, because if if there's a value in that array that's false, it means that I didn't see one number. There was some number I didn't see when I went across the row, down the column, and I used the same basic idea when I go through the subsquares. If any of those values are false, I can immediately return false because I know that this board is invalid. I don't have to check any other rows, any other columns, whatever, right? I don't have to check the subsquares, I haven't done that yet. As soon as I find a problem with the board, and again, this is sort of corresponds to how you would do it as a human being. You would, look through the board, you find a flaw, it's like, I don't need to keep going, I just circle it, hand it back to you and say your board is not correct. Now here's the slight change that we can make, just for fun. I actually hadn't thought about that, so here's the idea, and this will eliminate this extra loop that I had to have right here. When I create the array, all the values are false. Down here, I'm setting one value to true, but if that value is already true, it means that the board is invalid, right? Because if I mark one number as true twice, it means that there's another number that I'm never going to mark as true, right? So imagine the idea is that like I'm going across the row and the first two numbers in it are 1. I can stop right there, right? I know that there's no way this row can be valid because it has to contain every number, and there are 8 numbers left that it needs to contain, 2 through 9, sorry, and there are only 8 spots, right? There are only 7 spots, right? I've seen 2 numbers, they're both 1. 7 spots left, 8 numbers that need to appear, not gonna happen, right? And so what I can do is I can say if scene board I, j, -1, sorry. I gotta make sure everything is closed up here. Return false. And then if I do that, I can actually eliminate this whole other loop. So this is kind of a, maybe if I go back and re-record this, I'll add this, which I need to do anyway because I think there was a bug. But anyway, so this is a small optimization because, like I said, as soon as I see a number twice, I know it doesn't matter where in the row or the column or the subsquare I am. I know there's another number that's going to be missing farther down the line, right? Again, it's sometimes known as the pigeonhole principle, right? I've got 8 boxes, 8 values. Sorry, 9 boxes, 9 values. Every value goes in one box. If one box contains 2 values, there's going to be an empty one at some point, right? So I don't need to wait. And so this actually accomplishes the same thing. Questions about that approach? I mean, I think if you understand this modification, then you're definitely on your way to understanding kind of what that array is for, right? But just from a metaphorical perspective, right? If you want to think about like checking the board as like a human being, think about, and again, you're being very, when you think about how to design a computer algorithm, if you're trying to think about how you would do it as a human, you have to be very mechanical, right? You can't be like, well, I'll just look for the numbers 1 through 9, because you're using your memory, and the computer doesn't know how to do that, right? So you have to be very, very mechanical. So in this case, what I would say is, if you had, if you had something where you had a series of checkboxes, and you wrote down like, seeing, and again, maybe I can just do this quickly. This will be kind of silly, but. Let's see here, right? And this is just sort of a dumb example, but I'm going to use like just a little list here. And so here's my array when I start, and it's just going to be all false. And doesn't start at 0, so that's okay. So when I start going down the row, I initialize this to all false. When I see the number 3, I change this to true. Now I see the number 6, I change this to true. Now I see the number 8, I change that to true. Now I see the number 2, I change that to true. Now I see the number true again, and I see that it's already true, and I'm like, you know, not okay, right? Because it doesn't. I know that it doesn't matter how many, what other values are in that part of the board that I'm checking. I'm not going to get all the boxes checked, right? If instead of seeing 2 again, I saw 1 and then 4 and then 7 and 9 and then 5, I would keep going and I would be happy because I didn't see any value twice. 9 values, 9 slots. If I don't see a duplicate, and I know they're all within 1 to 9, that's really important too, right? If I didn't know that they were all in 1 to 9, I might have a situation where I would either go off the end of the array, like if someone put in a 0, I would try to insert it at index -1, which wouldn't work, or if someone gave me 22, I would try to insert it at index 21, which would also not work. So this is really all very much predicated on the idea that I've checked the board already, and I know that all of the integers that it contains are in the range 1 through 9. So hopefully that helps. Yeah, but I mean, this is cool stuff, right? I mean, it's a neat, and I think, again, this is a problem where, because we're working with something that people actually do using their mind and their brain, there's sort of nice analogs, right? In terms of thinking about, okay, like there's a famous, I'll put this in the, there's a famous video, my, old friend from graduate school, David Malin, who teaches CS50, he has this sort of funny video where, and I don't know exactly how this ends, right? But it's kind of like he has people come up and tries to give them instructions. Basically, have the class try to give them instructions about how to make a peanut butter sandwich, but it has to be like as if you're talking to a computer, right? And the computer doesn't understand. It's like, put the peanut butter on the bread. I take the can of peanut butter and put it on top of the piece of bread. It's like, well, you told me to put it on the bread. I took the peanut butter and I put it on the, So anyway, I mean, that's spread jelly on the bread. Well, I spread on one side, on the other side, on the sides, right? There's a funny, I mean, it's a little darker, but there's a when people talk about kind of the unintended, I think this is a quote from the Coder's book. People talk about sort of the unintended effects of computer algorithms and artificial intelligence. One of these sort of doomsday scenarios that people think of is, if we had a really powerful AI and you told it, maximize the production of paper clips from this factory, right? It might, and it didn't understand that there were other goals that we also wanted to pursue. It might destroy the entire planet and wipe out the human race in an effort to increase the production of paper clips, right? Which of course aren't going to be as useful when there's no humans to use them. But anyway, the idea is that computers are extremely literal, and if you want them to do something, you have to be very, very specific about how to do it. Now, again, once you can explain it to them, they're this incredible, powerful, genie-like thing that can do stuff incredibly quickly, incredibly fast. So sometimes I think of computers as almost like the world's dumbest genie, right? Incredibly powerful, incredibly fast, but incredibly stupid, right? Like you just have to tell it, explain it. People say, explain it like I'm 5. Explain it like it's a computer, right? You just have to be very specific about how to solve a problem. Once you can do that, you're off to the races. All right, if there are no other questions, I think I'll stick around for 2 minutes before closing up shop, but and hopefully that was helpful. Like I said, I'll probably go back and re-record at least this part of it because I like this new approach. I think it's kind of neat. At least it should be a footnote in terms of, because I think this sort of forces us to think about how we're using that Boolean array. But it's a small improvement. Other questions? If not, I think I will peace out for today. I hope everybody's doing okay. Take care of each other. I will be back tomorrow, same place.